welcome back to this course on computational thermodynamics and kinetics of materials. In this class, we will see how to use CalFAT tools to get some insights for doing alloy design and for microstructural characterization. Let's first see the alloy design part, where we can get certain insights for compositional design of, for example, in high entropy alloys. We saw what are these high entropy alloys in the last class. Selection of alloy systems is what we will be focusing on, because the last class I talked about high throughput calculations. There the selection of palette of elements is the first step. Okay, for that we need some literature knowledge. Okay, there certain insights from CalFAT can help. Let's see what are they. Okay, let's say the target is to achieve single phase solid solution. Okay, something like a single FCC or single BCC. The advantage is, this solid solution is a strengthening mechanism, because if you make a material from rather than pure element as solid solution, the dislocation motion can become difficult in that and the material gets stronger. And more importantly, the solid solution strengthening has an advantage, precipitation strengthening or even grain boundary strengthening. These things can disappear at high temperatures. At high temperatures, the grain may grow, the grain boundary strengthening is lost, precipitates may dissolve, they may not be stable at high temperatures. So these are problems with the other strengthening mechanisms, whereas solid solution strengthening can be there even at high temperatures. Okay. So one method to get some insights into selecting these compositions, selecting this alloy system, is inspection of binary phase diagrams. It's reported in this work. What it says is select elements such that the binary subsystems with a large homogeneity range for the targeted solid solution structure. For example, let's say target solution is FCC. Okay, two binary systems are given here: cobalt nickel and manganese nickel. And in that FCC region is given a very large FCC region from left to right. In this manganese nickel also FCC region is quite large, although not as large as this one. So if we combine these two binaries, CONi, M and Ni, so nickel is common to both. So if we make CO, M and Ni alloy, these three elements if we select, then there is a high chance that we achieve single FCC. Okay. So binary subsystems, so CONi and M and Ni have a large stability range for FCC solid solutions. Therefore, combine them and make CO, M and Ni alloys. If that is done, we can say single phase FCC is favored in such a system. So this tendency to FCC formation is sensed based on this analysis. In that we can select particular compositions which give the best FCC range or which has the lowest amount of costlier elements like cobalt. Those criteria can be applied to that. But what are the initial elements to select? CO, M and Ni. They can give single FCC. But this is only 3 elements. Which fourth element can be added? Now let's look at two different diagrams. So these are two different diagrams now. Cobalt chromium, chromium manganese. Okay. So here if you see FCC region is this much, BCC region is large, and the sigma phase also comes here. And here if you see even bigger BCC region, FCC is a very small region here, and sigma phase is also there. So these chromium containing binaries, they have this large BCC range and also sigma formation tendencies. Okay. Target is FCC solid solution. In that case, binary subsystem COCr, CrMn, these things favor BCC and even sigma. Therefore, chromium containing binaries may be rejected while FCC is targeted. That's what we can sense from the binary diagrams. But experimentally, people have seen that even up to 25% chromium dissolves in FCC to form COCr MnNi alloy. Okay. Last class also we saw about this particular alloy. Experimentally, it is shown that this alloy is a single phase FCC. How? Instead of checking only binary diagrams, we can inspect Gibbs energy data to get more insights. Let's see how to use that. Okay. First, we can apply that even to this question. Okay. CONi and MnNi we said have a large stability range for FCC solid solutions, right? Here and here. So which of the two binaries have more tendency to stabilize FCC? You may think that here FCC is smaller, here it is a larger range. Therefore, cobalt nickel system can be a strong FCC stabilizing binary. But if you look at the Gibbs energy composition diagrams, let's say this is at 1000 degrees Celsius. For cobalt nickel system, this is the Gibbs energy versus composition diagram. where you can see FCC curve being the lowest compared to BCC at all compositions, and obviously FCC is favored if this binary is added to any system. Now if you look at M and NA system, there also FCC curve is the lowest for the predominant part of the diagram, but the important comparison comes with the y-axis values. If you look at here, 0, this is minus 10, so somewhere near minus 7 or so is the mixing Gibbs energy change. If two pure elements are taken in FCC structure and mixed, the reduction in Gibbs energy happens to about minus 7 kilojoules. Okay, but if you take here manganese and nickel, this is about minus 16. Okay, so compared to this FCC is much more stable. So M and Na is a much more FCC stabilizing system compared to CONA. This insight comes from Gibbs energy composition diagrams. The actual values of mixing Gibbs energy changes. They tell you which elements tend to mix in FCC structure more. In that case, M and Na is a strong FCC stabilizer. Okay. So now this question that we have asked, combining chromium containing binary systems, FCC is less favored over BCC or sigma. Okay. If you look at the binary diagrams for cobalt chromium and the chromium manganese, binary Gibbs energy versus composition diagrams, you can see that FCC is here, the solid line, and below FCC couple of phases come here, that is BCC and sigma. Okay. Here also in chromium manganese also FCC curve is here, and below FCC this A13 sigma BCC, all these phases are appearing. Okay. But the distance, if you see from here to here, it is only minus 2 or 3 kilojoules. Here also it is possibly minus 1 or 2 kilojoules. So in that way FCC is very closely competing with BCC. This is an important idea. That is asking how close is FCC in the stability competition. In the presence of other FCC stabilizing binaries, how easy it is to suppress other phases, because other binaries, the cobalt nickel or manganese nickel kind of binaries, if they are added along with these binaries, then there is a very strong FCC stabilizing tendency. Is that tendency good enough to suppress this BCC? So this is an interesting question to ask. So quantification can be also done if we go for this kind of lines. Let's say here at 50-50, if we add chromium nickel to an alloy in equiatomic ratio, we can look at this diagram at 50-50 and see what is the Gibbs energy here. If this value of energy here itself is low, okay, G system, if this itself is low and it shows FCC, there is a strong tendency for favoring FCC. So that is there. So that is one quantity we can use. But more than this kind of quantities, if you take this cobalt chromium system where we saw FCC in close competition with BCC and sigma, here as for sigma phase it is drawn. This dotted line is sigma phase, and if at all this 50-50 composition stays as FCC, what will be the Gibbs energy? This G prime. And from there, if sigma has to nucleate, what is the driving force? Distance between this G prime and G double prime. So that is driving force for sigma. If this driving force value is small, then it is easy to destabilize this sigma and stabilize FCC. By adding the right FCC stabilizing elements to this, we can stabilize FCC and suppress sigma. And this is one more type. D of FCC is G prime minus G double prime. This is a slightly different way to quantify the competition. If at all this 50-50 composition is in BCC structure like this, from there draw a tangent to FCC line, FCC curve, and see the distance. So this is in a way making FCC stable from this BCC. So this is G prime minus G double prime. It may be a positive value, but if that value is small, then it is easy to stabilize FCC. So that can be checked. So this is something that we haven't discussed till now. The FCC curve can have this kind of shape. Here in all these cases it is completely convex. So what if it has it in this kind of concavity? If it has this, then if you try to mix two elements in equiatomic ratio, let's say, and make one single FCC, its Gibbs energy will be this high. Okay, if at all that FCC breaks into two different FCCs of this composition and this composition given by this common tangent, then the system will be stable. So the distance between this to this is quantified here as delta G50. It is the tendency to unmix. If this tendency is small, then unmixing will be less. What if this tendency is small and we add other FCC stabilizing elements? then it is easy to suppress this tendency to unmix and make the elements mixed in a concentrated manner. And that is possible. So in all these cases, this driving force becomes an important idea to analyze, and that can give lot of insights about what can be stable, what can be metastable, and how easy it is to achieve the metastable phase and things like that. Okay. With this sort of insight, if you see this quote by Olson, we tend to think of thermodynamics as something that applies only to equilibrium. But the truth is, it wouldn't be called thermodynamics if it was only about equilibrium. It was created to describe heat engines that are highly dynamic systems. In modeling them, it is useful to look at equilibrium limits. But really, the power of thermodynamics is it describes the driving force of dynamic systems, and it really drives the evolution of microstructures and processing and service. So in fact, I prefer to describe CalFAD as calculated phase dynamics. That's wonderful. Okay, now let's look at how CalFAD can help in characterization. Okay, so this is cobalt, chromium, copper, manganese, nickel alloy. We saw this in the last class, and this kind of diagram is the phase fraction plot for this system. And at 1000 degrees Celsius, if it is heat treated, what we get as number of phases, their fractions, compositions, they all match well between CalFAD and the experiments. You can see the CalFAD phase diagram, phase fraction plot here that shows two FCC phases, FCC1 and FCC2 at 1000 degrees Celsius, and calculated and experimentally observed composition of phases in this alloy after heat treatment are given here. So you can see the calculation results for FCC1. These are the compositions. Experimental composition comes very close to that. Okay, for other phase FCC2 also. And in microstructure we see copper rich and chromium rich phases. So this phase is rich in chromium and this phase is rich in copper. So that also matches very well with the experiments. Okay. So you can get this information, phase fraction and composition of phases from CalFAD, and then look at the microstructures. You already have a very strong roadmap for you to understand the microstructure. Okay. This is another interesting example, cobalt, niobium, iron alloy, not giving the exact composition here. Before assistance from CalFAD, this is how the XRD is analyzed. Conventionally, people go for this XRD database and try to match which phases match the best. Okay, or trying to identify structures, especially for simple structures, people are ready to do this for BCC, FCC, things like that. When things get complicated, phases get complicated, that method, using that method will become really difficult. Okay, this is how this alloy is initially characterized. This is after 1 hour of mechanical alloying that particular composition, and after some time, 30 hours, it is like this. And when SPS is done, spark plasma sintering, this is how the microstructure is. This is how the peaks appear, and they are characterized as 4 different phases, one BCC, 2 FCC phases, and one FeMO2 compound phase. This is how it is initially characterized. But the moment CalFAD is done for this, and then it is used for assisting this characterization, you can see here. We have these phases: BCC, mu phase, C14 Laves phase, and liquid. These are the 4 phases. So in the solid you have these 3 different phases, and when XRD is analyzed carefully, we see that these phases appear. Okay, the peaks may be slightly shifted. I will explain about that shortly. But in this case, at least we have this phase fraction plot which is showing these phases. When one tries to match these phases, more or less they are matching here. But if we do not have this kind of phases coming, what if they are not even there? The entire system is studied for the first time. Even CalFAD doesn't have the database. Then how to go about it? Let's see one example like that. This is a hypothetical example I am giving. So let's say XRD pattern looks like this for a particular alloy. It is not explored at all. It's in a ternary ABC system. It is unexplored in ternary regime. Binaries are explored. AB, AC and BC binaries are explored. Let's say. Okay. So an alloy in this system is made by mechanical alloying, isothermally heat treated at temperature T1 and quenched and characterized. Okay. It has grain sizes in the nano regime, let's say less than 100 nanometer. Therefore, identifying the chemistry using the EDS analysis and all will be really difficult for this. Okay. So XRD, widely followed conventional phase identification method is this, where use the best matching pattern from the XRD database. Okay. But it can be misleading, especially when higher order extended phases or new emergent phases exist in the alloy. But CalFAD will be useful at least to identify these extended phases to some extent. How CalFAD can help in identifying such phases, we will see that. Okay. So I am now putting colors for that pattern. some of them are in orange, they belong to one phase, and these blue lines belong to some other phase. Let's say a couple of phases are there in that system. Okay, so A5B, let's say this is one compound, it is actually present in the alloy system with some C dissolved. So this is a binary side AB compound, but in that C element dissolves to some extent. Okay, therefore it is an extended phase to ternary region. Okay, it is a stable phase in the AB system. A5B is a stable phase in the AB binary system. Therefore, the standard peak of this compound A5B should be shifted due to carbon dissolution. What I am saying is this. So, if you bring these parts, these are the actual positions of peak positions of A5B compound, the binary compound I am talking about. They lie here, but because of the C dissolution into this phase, all these peaks are shifted. Okay, let's say the C being a larger element, it increases the lattice parameter. Therefore, all the peaks should be shifted to left. Okay, so this shifting will happen. However, XRD database is not available for this extended phase. These peaks, these positions will not come in the XRD database. Therefore, only going with this binary A5B pattern shows a poor matching with the observed pattern. Obviously, like this, there is a severe mismatch, right? And hence it is rejected. This particular phase, because it has very less matching, it is rejected if you follow the conventional method. Okay. So therefore, a misleading characterization can be done. The best matching patterns of other phases of certain ABC compositions are mistakenly chosen, which are actually not present in the alloy. Just because they have a good matching with this pattern, they may be selected. So that is wrong. Okay. So what to do then? Let's see what how CalFAT can help. A5B with carbon dissolution is not included in the CalFAT database because this entire ternary system itself is not studied yet. So CalFAT equilibrium calculation need not show it. So this is a problem now. Then what to do? What are the options? One, equilibrium calculation shows certain phases. Then check whether their XRD patterns match with some shifting. Okay, so like this is a binary. The binary may be shown in the equilibrium phases. You take that and see whether that is shifted. So this shifting, one has to think how much of C would have been dissolved. If so much of C is dissolved, then how much will be the shifting in the phase. So this has to be guessed and tried out. Okay. Second is check all the phases in binary subsystems AB, BC and AC. Okay. Then get their Gibbs energy composition curves at this temperature of T1 where the heat treatment or SPS is done. Then find the hierarchy of phases from the lowest to highest Gibbs energy and take them, try matching their XRD patterns in the same order. What we are talking about is take AB binary, BC binary and AC binary. See what are the possible phases in that, the stable phases in the diagram. Collect all of them. For those phases, see how the Gibbs energies are. Then get the phases in the hierarchy of Gibbs energy, the lowest to highest Gibbs energy, and then give preference to the phases which are having the lowest Gibbs energy. Try matching their patterns first with some shifting. In that way, CalFAT can help. If not G versus X diagram to get the hierarchy, at least the binary phases from the phase diagram should be considered before sitting for analyzing the XRD pattern. Most of the times, especially with these kind of elements, cobalt, chromium, iron, manganese, nickel, or the refractory elements like molybdenum, vanadium, titanium, zirconium, tantalum. Within these elements, if you see, there are not many new emergent phases in the ternary or in the higher order region. Most of the times, what you get is the extended phases from the binary region. So therefore, we can characterize them based on this help from CalFAT quite effectively. Okay. Thank you. I hope the lecture is useful. See you in the next class.